Hello again, it's Cliff here. Yet another exciting episode of RapidTurn. I think this is episode 8. Just a quick recap on the Spindle issue that we talked about in episode 7. I don't think I will be breaching any of the communications confidentiality with Tormach if I say the following, that they have posted to a public forum. They've posted to a forum CNC Zone, the Tormach section, under the thread RapidTurn videos. They've posted the following content, that Tormach are aware of the problem, and that there has been a problem with production to date, that the factory specifications were incorrect, and the spindles have been made incorrect to date, and they've now rectified that with the factory, and the factory are now producing to the correct specifications, and that the RapidTurns that have been sold to date, Tormach accept responsibility for that. They will contact the buyers. They're currently deliberating as to what is the best way to rectify the problem, and when they've done that, they'll contact the buyers, and the problem will be rectified. So that's common knowledge. They've posted that to the forum. So just passing that on. You can have a look at the forum for the details yourself and that thread if you're interested. But basically, they've accepted responsibility and they will resolve the problem. So that's really good to hear. So now I can get on and get on with episode 8. Well, it might be a while before Tormach finally resolve the best way to rectify this problem with the spindle bore. Too much clearance on the spindle bore. Whether they decide to replace all of the actual spindles, or whether they replace the whole headstock assembly to the existing buyers, send them out to the existing buyers. I don't know what the outcome will be, but in the meantime, I need to keep my RapidTurn going. So what I've done, I think I've mentioned, is shrunk a sleeve onto the chuck arbor that is a close fit in the spindle bore, and fills up that 0.3 of a millimeter approximate gap there. Allows me to get going again. It doesn't solve the problem with the collets, but it gets me going with a chuck, and so that's an option just for the short term. Machined up a very thin wall sleeve and a little zone on the end of the shank and shrunk it on. Well, that was tricky work. The centers were burred over and I had to lap those and get it running true before I could do that, so it took me a couple of hours. But okay, I've got a close fit now on the arbor inside the spindle bore, and I can carry on with my development. At least use the chuck. I just can't use my collets. So my chuck arbor has now got a sleeve shrunk on here, a close fit on the 5C bore, that clearance diameter inside the bore of just over 32 millimeters diameter. So that's a nice snug fit in there now, so it can't rattle around, as I've mentioned in my previous video. So I've got a little alignment mark here on the end of the spindle, and another alignment mark here on the flange, so I can align it each time in the same position. There's a good reason to do that, so that you get repeat accuracy. I noticed little bits of swarth were going into this beautifully made little key slide lock, and so I just put cheese head screws on in place of the round head screws, and just cut a little plastic box to go over the top. That'll do in the meantime till I think of something a bit tidier that won't rattle off, and just to keep the metal particles from flying into that precision slideway. Don't want any more in there. So the chuck arbor or adapter is now mounted securely in its position and tightened up firmly, and I've taken a light skim cut with this carbide tool. The chuck arbor is actually hardened steel, about 50 Rockwell C by the feel of it, but carbide will handle that if you take the light cuts, not too high in RPM. So now it's running beautifully true. Okay, so then we mount the chuck. We incredibly lightly nip the screws. They're little more than finger tight. I've marked the chuck to the flange with a little marked position, so I always put it back that way. Also, it's a really good idea to mark a particular scroll pinion, because if you tighten only with that scroll pinion for accurate work, it will repeat much better. So you just tap it very lightly. You don't want to tap it firmly because you could Brunel the spindle bearings. So you're talking very, very light taps to get it true until it's, I think you can see there, it's running nice and true. And then firmly tighten the mounting bolts, in this case with the ring spanner. There. Just back off the focus a little bit. So the reason why I say to mark one of those scroll pinions is because if you now tighten with another one, see I've got it running perfectly true there, very true, in fact probably as true or more accurate than some collets will achieve. Now if I tighten up with a different scroll pinion, tighten it up, you can see now we're running out 500ths, that's 2 thou run out. And you say, well, why would that be the case? The scroll pinions shouldn't affect it. You know, because then when you first look at it, you think, no, that wouldn't do it. You tighten with the same scroll pinion that we originally clocked it up with, it's now running true. So why is that? Well, the reason is because the scroll is never a perfect fit on its bearing, and when you tighten a particular scroll pinion, because of the thrust of the pinion and contract gear wheel, it causes the scroll to rock off center one way or another, and so as long as you're tightening the same scroll pinion each time, you get repeatability. So I always mark the one that I want to use for tightening if I'm doing precision work, and then you can get repeat accuracy with a 3-jaw chuck in the same kind of league as a collet. Sorry if I'm telling grandmother how to suck eggs here. I'm sure a lot of you guys already know this stuff, but I just thought I'd fit it in while I'm doing it. So now we have one high precision, increased capacity 3-jaw chuck. I love it. Well, while I'm thinking of it, just a little safety tip. Some of you might have had your Z stepper brake fail and the head just starts sliding down when you power off. It's happened to me a couple of times. Doesn't happen very often. If it's never happened to you, you might not be prepared for it. So be prepared for it. What I've got is a little block of acetyl, but it could be wood or aluminium. And when I power off, should that ever happen again, I can just grab it out and hastily put it underneath the head coming down before the cutter or whatever crashes into the table. Just a little safety tip there. Some of you have been asking about, great to see that you can do the gang tooling and the automatic positioning from different tool stations, but how do you get PathPilot to generate those positions? How do you get PathPilot to do the offsets when there's not really a facility for Y offsetting within the software that you can see? Well, I'll go through that briefly now, but I'm not an expert on programming and software. I come from a mechanical engineering and tool making background, and I would rather experts in that field that can speak with authority went through that with you. People like Daniel Rogi of Tormach have already got some excellent videos explaining how to set your work offsets and tool offsets and so on. So I'll just go through it really briefly. just to kind of fill in the gaps, and hopefully somebody soon will better explain how to do it than I can. This is an area that I've learned about more recently in life and I'm not an expert on. Okay, so I'll just skim over it quickly first of all to give you an overview. So if you've watched some of these videos on Slant Pro and RapidTurn as to how to set the tool offsets, you'll know that per tool you select the tool number and you touch off the X and the Z. So you're establishing the relationship between the software, the tool and the work for X and Z. But there is no real facility for Y other than this very small DRO here. So I'll just explain to you now and fill in that gap. How do we do the Y? Okay, so let's say we've got the master tool, which in this case is this tool. We set the X and Z just as you do normally, and then set the Y as well, and enter here on the Y DRO 0. Now that's what I would call the master tool master Y position. Now I would then jog over with the other tools that I want to use, parting tool, center drill, boring bar, whatever it is, and find the Y position. Now you might just use a pointer, for example. That would get it roughly right. And then write down, so here we have T1, I'm calling it master tool, Y0. Then we're going to go to the center drill, Y121.2, and we're going to go to a drill, a 9mm drill, that's also 121.2. Then we go to the back, to the parting position, that's minus Y, minus 81.08. Okay, so we produce our code, just back off a bit here, in the normal way using the conversational and a pen to file, produce a long string of code, various operations. Now if you were to just run that code, it would all be in the same Y position, because the PathPilot software doesn't have the facility to easily produce different Y positions as part of the conversational. So what you do then is you produce the code and then go into edit G code. Okay, and right at the beginning you put in there, if it's not already in there, GOY0. So that sets it for the master tool. Then when you come down to the part of the software, part of the program that says, okay, we're now going to start doing the center drill, for example, this is it here, we've parked the tool and the tool changed position, and we set the revs, we put the coolant on, and we're going to the initial starting position, GOX, GOZ. Well, just in there, it's here, put in GOY in the position 121.2, and then carry on down with your program until you see the next tool change position where a Y is needed, and then you just put in there GOY minus 81.08, for example, and then right at the end of the program put in again GO, or at the beginning of the program, GOY0. So what I'm doing is just manually installing those Y tool changes. Does that make sense? That's just a quick overview of how it works. When I actually do a job, a paid job, see, this little plastic part that I made was just to test it out. I don't want to spend a lot of time doing different parts and going through it all in detail until I've got either paid contract work, or I want to make a run of parts for the next production run of probes. This is one of the reasons why I've got RapidTurn, so I can machine some of the internal circular lathe produced parts. Then I will take a lot of time over setting it all up and do some videos at that time explaining it in depth. But at this stage, that's just enough to get some of you going, because I know some of you are seriously thinking of buying RapidTurn, but you're just a little unsure as to how the different Y tool station gang positions can be programmed. Cheers. While I'm working on RapidTurn, my other 1100s doing a contract CNC job, I just wanted to show you graphically the advantage of the back splash guard on the table. I've got really high coolant flow going, and you can see that back splash guard is keeping most of it off the machine and keeping the metal chips away as well. It just fits nicely under that gap under the head. You come around to here, you can see I've talked about this in previous videos. It's a real advantage to stop that area where the bellow covers are from getting full of swarf, because when the slideway goes back it gets all bunched up and then it will eventually split those bellows. So I do two things there. I have a back splash guard which fits nicely under the head. Oh, it's awful blurry there, I know. And put a rag on top of the bellows to stop the swarf from getting down inside them, because really it's important. Underneath there the ball screw is exposed, and any drips of coolant carrying dirt will end up on the ball screw if you're not very careful. Trying to find a place where it's not too blurred out, because if you're like me, you love watching metal being cut with a CNC. It's such a cool process. Here's my high flow coolant system. Got a big pump motor, and it's filtering back through these synthetic cloths. Oh, spray going on the camera, that's never good. Better stop this. And another thing I might have mentioned in a previous video is it's a good idea to have a little spout on the outlet there so the coolant flows clear of the table slideways. If you don't have that, the coolant will run underneath the table carrying the chips with it and onto the tercite type slideways, and that's really not a good idea. One thing I've found since I've been getting into CNC that if you can do a 3D part with as much 2D tool path as possible, and then just a bit of 3D blending, saves a lot of machining time. I just want to do a short clip on Tormach accuracy. I've had a couple of questions from viewers regarding the accuracy potential of RapidTurn and the milling machine, and I'll just do a brief clip on that now. On about video 4 I machined a long part between centers, and it turned it parallel to within 1/100th of a millimeter. That's less than half a thou. And I'll just do I've been asked to do this test, and I'll just do it now. A traverse between a dial indicator connected to the head and the table to show you how much you can expect the x-axis to droop with the weight of RapidTurn hanging over and doing a full traverse. Okay, so you can see the dial indicator there is on about 1 or 2 hundredths before the zero. And there, sorry, I'm kind of filming and looking at the same time, about 3 hundredths between 0, 3 hundredths, and 2/100ths. So it's only shifting about 1/100th of a millimeter in terms of table sag or error in the longitudinal table, or out of parallelness in the slideway and so on. And that's very good. That's very good for a dovetail slide machine. In fact, it's far better than my manual milling machines. Well, again, we've probably got enough clips for episode number 8 to be compiled. So that was fun. Thanks for watching, and I'll put this together. Cheers.